We've just been looking at balanced equations, balanced reactions, and using these coefficients to say how many of each atom we have. So we're going to practice that in a lot more detail on this next slide. So we are going to balance our reactions. As we balance reactions, remember that the atoms on the reactant side have to be exactly equal to the number of atoms on the product side. And then one other thing that we have going on here is some types of reactions. This is just classifying kind of the patterns that we see here. Just like you classify in math addition problems and subtraction problems. Here we're going to classify our reactions as combination or decomposition. So we're going to take them one at a time. This is the 5 different types of reactions you have to know, and then we'll have a bunch of practice balancing, and then you'll have more practice on the next page to do on your own. So first of all, there are typos on this page, so there should be a subscript 2 here, and this 3 should be a 2, so I apologize for that. But now that we've fixed that, we are going to first look at the type of reaction and then balance it. So this is a combination reaction, and combination reactions, if I can kind of put it into sort of like a math format, will be A plus B turns into a compound made out of A and B. All right, so A separately plus B separately gives me the compound, and that's that same reaction we saw on the first page. Sodium plus chlorine turns into sodium chloride. Now, when I go to balance these, there's a lot of different ways to do this. I won't ever ask you to show your work, but especially if you're new to this, it's good to be able to show your work. I'm going to try and be very neat as I do that and methodical. Neat and methodical are really helpful in any problem solving situation. So I'm going to look at this reaction, and I'm aiming for equal atoms on both sides. So I'm going to do what I call an inventory underneath it, and I'm going to grab a different colored pen. So I'm going to say here that I have 1 sodium, and I'm counting my atoms here in red. When I see this Cl2, remember that that's this molecule, so I'm going to count this as 2 chlorine atoms, or 2 of these green atoms. And then through the middle here, this is going to be where I say, okay, this side needs to equal this side. So now I'm going to count what I have here. I see that I have 1 sodium. So this is just 1 sodium, so like this. And then 1, put it next to it, 1 chlorine. All right. So now that I have taken my inventory, counted my atoms, I want to compare the 2 sides. All right, I see that I have 1 sodium and 1 sodium. That's good, because I always have to conserve mass, right? That's a law of nature. 2 chlorines and then only 1 chlorine here. So I see that those are out of balance. So I need to add a factor or a coefficient to fix that. So if I have 2 chlorines here and only 1 here, I can add a coefficient out in front of that sodium chloride. And notice this 2 is a factor that goes to the sodium and also to the chlorine. So I'm going to take that 2 and I'm going to say now I have 2 sodiums and now I have 2 chlorines. All right, that's the significance of that coefficient, or that 2 out in front. Once I've added that, which was designed to fix my chlorines, now I have to check everything again. 2 sodiums, 1 sodium. Those are out of balance now, right? If I have 2 here, I need to balance that out by saying that I would have 2 here. And so when I change that inventory, now I have 2 sodiums. I think I'm done, but let's double check. 2 sodiums, good. 2 chlorines, good. So this is now what I would call a balanced equation, and you might add a 1 in here also to say, hey, I have 1 of those. It would be wrong to say that I have 0, all right? Now, quiz or test, you might just simply see this as your answer. We don't have to show all this work, but this is how I kind of thought through my work, all right? Next reaction down. So let's take a look at decomposition. So decomposition is going to be exactly the opposite of combination. We take a large compound and we're going to decompose it or break it down into at least 2 separate compounds. All right, this actually happens inside of airbags. This is, or in old airbags, this was an explosive that then breaks down and gives me these 2 elements. So same as I did before, I'm going to take an inventory first. So I count 1 sodium and subscript 3, so that's 3 nitrogens. Notice there's an inferred 1 here, so this 3 is just for the nitrogen, all right? And then that's going to have to be equal over here to 2 nitrogens and 1 sodium. All right. So as I look at this, it doesn't really matter where you start. I just strongly suggest that you start somewhere that feels easy in terms of balancing. So as I look at this, I say, okay, sodium's good. And then I have 3 nitrogens and 2. That's not as easy as a 1 and a 2 to work out. So when I see a 3 and a 2, a little trick you want to do is think 3 times 2 is 6. So I'm going to make my goal to have 6 nitrogens on both sides. So that means I'm going to put factors or coefficients that help me get up to 6. So if I want 6 nitrogens and I have 3 times what gives me 6? Hopefully you came up with 2. And then if I have 2 nitrogens, 2 times what gives me 6? 3, hopefully. So let's update our counts here. So this is now going to be 2 sodiums. And then here I have 2 times 3, so I have 6 nitrogens. Over here, 3 times 2, I have 6 nitrogens. Okay, so this is just kind of my scratch work, my organized work down below. So sodiums, I have 2 and I only have 1 here. Nitrogens, 6 and 6, so I need to balance my sodiums to finish up here. I'm going to say 2, so I need 2 here, and that means that I change that. And so this is my final answer, 2 and then a 3 and then a 2. And that is a decomposition reaction. Next up, single displacement, or sometimes you'll see this written as single replacement instead. So here I'm going to take compound A, or element A rather, plus a compound, and the A is going to replace the B. Single element replaces another one. And so I end up with B all by itself, and now A has combined with C. So here's my single element and a compound becomes a new compound, and then there's a single element here. Okay, and where I have these products, if I wrote silver ahead of the copper nitrate, that's fine. I can switch that around. So I have something new here. Notice that nitrate has shown up, and it's on both sides. If you have a balanced equation where you have a polyatomic ion like nitrate on both sides, just keep it there. Don't break it up into nitrogens and oxygens, just keep it as an NO3 package deal. So here's what I mean when I go to take my inventory. I have 1 copper, I have 1 silver, and I have 1 NO3. Okay, keep that polyatomic together because it's on both sides. Over here I have copper and I just have 1 of those. I have 2 nitrates, so I'm going to write that as 2 NO3s, and then I have 1 silver. And if the tightness of this is hard for you, write it on a bigger paper where you have even more space. Space helps us learn sometimes. So now I'm ready to balance. All right, I've got my inventory. Let's see what I can balance. So coppers are good, 1 and 1. Silvers are good, 1 and 1. Nitrates, I've got 2 here and only 1 here. So that means I need a factor of 2 here, which is going to change this to 2 silvers and 2 nitrates, right? 2 of each of those. So now my nitrates are good, but in the process, my silvers need some help. All right, so silver, I'm going to put 2 here, and that changes this 2 here. And if I check through this, 1 copper, 2 silvers, 2 nitrates, that's going to be my final answer. All right. Notice there's no phases on any of these, the solid, liquid, gas. If there were, you could ignore them. They don't have any impact on how I'm balancing my atoms. All right. So we've got 2 more reactions to do here. Double displacement reactions are going to be some of your biggest, most complicated ones. So that would be A plus B, or AB plus CD. And now I have a double compound and a double compound, and the A and C are going to switch. So I will end up with AD plus C is now connected with B. So the A and the C have flip-flop partners. They look kind of complicated, but you can do this, all right? So let's take our inventory. 1 iron, 2 chlorines, 1 sodium, and I hope you recognize that hydroxide is one of those polyatomic ions. Because I see it on both sides, I'm just going to keep it as hydroxide, all right? Here I have 1 iron, 2 of those hydroxides, 1 sodium, and 1 chlorine, all right? On the outside chance that all of these matched each other, you would just put 1s all the way through, and you will see that sometimes. Don't get thrown by that. Here I can see there's a couple of mismatches though. So I can see iron is good. I can see I have 2 chlorines on this side and only 1 here. So I know I'm gonna need to double that, all right? Which has now doubled both my sodium and my chlorine. I can also see there's a hydroxide problem, 2 here and 1 here. So I'm going to fix that by putting a 2 here. And you'll get better and faster at these as you do more. And so now I want to double check. 1 iron, yes. 2 chlorines, yes. 2 sodiums and 2 hydroxides, good to go. All right. Last reaction, and the last type of reaction as well. Combustion is going to be some kind of fuel plus oxygen. We saw this in our very first chapter. Gives me carbon dioxide and water and our good friend energy, right? When we burn things, that's the whole point, is we want to get energy out of this. We aren't showing energy on these reactions yet, but just so you know, it's there. All right. So here, we've got some bigger subscripts than we've seen. Grab my color. 1 carbon, 4 hydrogens, 4 H's, 2 O's, 1 carbon, 2 O's, 2 H's, 1 O. So we have something new, and you're going to see this in your combustion reactions, that I have oxygen just in 1 molecule here, but I have oxygen in 2 places here. To me, that's like stressful. Okay, now I have 2 things to work on. So I'm going to leave that stress for later and do the easy stuff first. All right, and that's a good way to handle this. Balance what's easy, and then the harder things will sometimes fall into place. Okay, so let's just kind of work from left to right here. Carbons are good. 4 hydrogens, and I see 2 hydrogens, and I'm just ignoring those oxygens because they're everywhere. All right, so to fix my hydrogens, I need 2 here. That's going to be this 2 times this 2, so this becomes 4 hydrogens and 2 oxygens. All right, now I'm going to have to look at my oxygens. On this side I have 2, and on this side I want to add these 2 together, 2 oxygens and 2 oxygens. That's a total of 4 oxygens on my product side. So 4 oxygens on the products and 2 on the reactants. That means I need to take my reactant oxygens and multiply them by 2, and that will give me now 4 oxygens and 4 oxygens, and that balances out. So on the next page, there is space for a ton of practice. You can try some of these ahead. We'll also go over them in lecture.